Thanks for everybody coming out. I'll just set the stage and let my esteemed colleagues take over. I'm actually presenting one of the papers today on behalf of one of the team members. But let me tell you why the FDX amplifier stuff is important and kind of how it fits in the overall strategy. Because we all have some decisions as to what to do. So FDX is a technology really where you can, as you'll see in the panel today, reuse spectrum in the upstream and downstream direction. And that takes some tricky electronics, it takes some echo cancellers, actually takes some really cool electronics. But as it was defined in the cable labs, when we all went to define it, it was designed to work on an N+0 system, so a node with no amplifiers. Once it was done, the realization kind of came to everybody that we have to have an amplifier to deploy it. There's at least one company who's willing to deploy FDX in a node+0 system, but still there's only 10 or 20% of their plant that would ever be built to N+0. The majority of the worldwide market is N+2 or N+4. Now, in the beginning, our teams individually kind of started working on FDX. When we started in 2014, we assumed an N+5 plant, and we had an amplifier and a node in development. When the market decision was N+0, we had to put that on the shelf, and then we brought that off the shelf last year. And we were just 2 weeks away from getting it to kind of work with some demo results before the project got shut down because the market kind of shifted over to ESD. So we're in this kind of quandary where we're within the grasp of making FDX work on an N+2 and N+4 plant. Theoretically, it looks like we can do it. You're going to see some fantastic papers today that suggest what we can do with that. Is there a market for it? Are we going to go do it? Now, at the same time, that amplifier can also be used in the 1.8 gigahertz extended spectrum environment, because over there's some cool applications for echo cancelers as far as reduced guard band and stuff like that. So we present you this technology. The question for all of us to figure out is, what should we do with that? So with that, did you get an introduction yet?
I briefly introduced myself.
So here's a really smart guy from Nokia who's been working on the FDX with the larger DOCSIS team for a number of years now, and has written a really fantastic white paper that I think all you guys should read. So with that, I'll bring up Werner.
Okay. So first, a brief recap of today's situation. So frequency division duplexing uses these diplexer-based amplifiers, a sketch of which is shown here, where you use these filters to isolate the upstream amplification chain from the downstream amplification chain. And you have the upstream that occupies one frequency band, the downstream that occupies the other, and in between you have a guard band. Because of the limited steepness of these filters, you need that there. And the purpose of the filters is basically to avoid that you have a closed loop gain which is larger than 1, and these things are oscillating and you would lose the amplification properties. As John already mentioned, full duplex DOCSIS was initially designed for N+0 networks, and then only afterwards the realization came of we need some amplifiers, and that's what we're trying to talk about in this session. So I will consider 3 different types of amplifiers and address pros and cons of each of them. In trying to marry full duplex with amplification, so in networks containing amplifiers. The first one, and the simplest one, is a diplexer-based amplifier, which can be reused in conjunction with full duplex DOCSIS equipment. That means it has no echo cancellation and supports only frequency division duplexing operation across the amplifier. The second one is what we call an ALI cancelling amplifier, where ALI stands for adjacent leakage interference, meaning that it doesn't cancel the echo of a signal, but it actually cancels the echo of the noise, or the out-of-band noise of either the upstream or the downstream band, which allows you to put the bands closer together and achieve a near-zero guard band solution. The last one is an active full duplex amplifier, which is actually cancelling the echo of signals that overlap in frequency. That is an amplifier that supports the same kind of echo cancellation as you would have in the node to support simultaneous upstream and downstream signals on the same frequencies simultaneously being active. So that supports full duplex operation across the amplifier itself. And so the last two are what you call echo cancellation amplifiers. And they have some kind of different properties than the regular diplexer amplifiers, which I'll jointly address. So let's start with the simplest case. So a diplexer-based amplifier. In a schematic, what it looks like, if you look at both ends of the amplifier, on one end you have large upstream power coming out of the amplifier, a small downstream input power. You have no noise from your downstream being echoed in the from your upstream being echoed in the downstream because you had that filter there, filtering it all out. So you basically don't need to do much. You just take in the downstream signal, the upstream is filtered out as well, and you amplify it and you combine it back with a diplexer on the other hand, and vice versa on the other side of the amplifier. So it's pretty easy to list up the pros and the cons of such a solution. The only big con is actually, okay, you have the guard band. So you have a lost portion of the spectrum, and typical guard bands with current diplexer technology are about 20% of the maximum upstream frequency. So if you have a 492 megahertz upstream split, you add 20%, and then you have your first minimum downstream frequency. So in the table on the left, I show for the different split points from 204 to 684, the size of the guard band to show you how big that lost capacity is. And so you have the downstream capacity numbers there, which assume a 75% efficiency and 4K QAM modulation, so it's pretty simple to do the calculations. And you see that on the lower end, for 300 or 396 split, you lose about half a gigabit. For the higher splits, you lose a gigabit in capacity with that guard band. The pros, of course, is it's a proven technology that has been deployed for a year. Everybody's experienced in how to design an amp plant with diplexer-based amplifiers. It allows for high cascade depths, and I mean that relative to the other solutions which have echo cancellation, which imposes additional restrictions on the achievable SNR you can get with a single amplifier. So it's only thermal noise and nonlinear distortion you need to account for, as you're used to. Another pro is actually that you don't have any full duplex interference to deal with, so CCI, ACI, ALI, so co-channel interference with the overlapping signals at the same frequencies. Adjacent channel interference is the impact on the dynamic range because you have large power at frequencies that still comes into your receive chain, but you don't actually need. And ALI is that noise that couples in as well under your signal from an adjacent transmission. So none of that is present in a diplexer-based system. And so I also considered distribution system design with echo cancelling amplifier. So once you have echo cancelling amplifiers, you have this additional distortion you need to take into account because you will have a certain echo cancellation performance and you will have a residual echo. So for a certain return loss level, your amplifier with whatever echo cancellation design it has will have a certain limitation on its output SNR. And just as a matter of back of the envelope calculation, on the table below, you see on the left is the SNR that you would have with a hypothetical echo cancelling amplifier, so a range from 41 to 56, which would be extremely good. On the different columns represent the maximum amplifiers you can tolerate to have an end-to-end SNR above a certain level. So, and the second to last, the first to last, how in English, you second to last column of 41 dB, that's the SNR that you basically need to support 4K QAM. And so as an example, if you want to support 4K QAM and a cascade depth of 3, you need a single amplifier SNR that is able to produce in the downstream direction SNR of 47 dB at its output after the echo cancellation. So that is something that you need to take into account when you design with echo cancelling amplifiers, whatever their type. Then ALI cancelling amplifiers. What does it look like? So the big change here is that you see the upstream and the downstream bands have been moved closer together, and you have this noise of the, if you take the left side, of the upstream signal, which couples in under your downstream signal. So if you would amplify that without any echo cancellation, you basically amplify the downstream signal as well as the upstream noise. So you put the SNR limit at the output. That's not what you want to do, is you want to put some echo cancellation there to remove that light blue part, the upstream noise underneath the signal, before you amplify the downstream signal. To get at the output a good downstream SNR, and vice versa for the upstream, of course. I can take a hit at the numbers. So this shows a general topology of what a full duplex amplifier, how it will couple to the line. You have a certain hybrid circuit which couples the coax interface, which is popping out of the amplifier, with your transmit chain and your receive chain. And you have three characteristic losses that are very important there. One, so with a bracket 1, is the loss from your transmitter output, your PA output, to your line. So at the PA output, you have a certain upstream signal level and out-of-band noise that gets attenuated by that loss from your transmitter to your line. At the RF port, you have a little lower power. Number 2 is the loss you have from the line port to your receive chain. So you have a downstream signal at the input that you receive. It couples through the receive chain for amplification, but it gets attenuated by that loss from the line to the receive port. And then 3 is basically the most important quantity. That's the isolation you have from transmitter to receive chain. That has multiple contributions. One contribution is that of the hybrid circuit or the coupler. Typically it's a power splitter or a directional coupler itself. So you can have very good directional couplers with extremely good isolation, but that's assuming an ideal 75 ohm at the line port. So that's one contribution. Second contribution is you go through that circuit, so through the loss 1, then you reflect on whatever you have there in your amplifier. Surge protection, connector, that gives you return loss. And then it couples back through the path 2 to your receive chain. That's the second contribution. Then you have a third contribution, which is typically the most dominant one, because the other two you can design for internally, and that's the external cable plant return loss. That's what's out there. That's what the taps are being causing as reflections. That follows the same path. So transmit to line, you go on the cable plant, you reflect, and you go line to receive. And in this calculation, I took the return loss that we specified in cable labs for M+0, because we specified the performance of these devices assuming a certain echo level. That's crucial for echo cancellation. You cannot predict or say anything useful about performance if you don't say with what return loss or with what echo that performance was achieved. So for that reference cable plant return loss, which I plot there below, you can calculate actually that the so-called required echo cancellation depth, which is the difference between your echo if you wouldn't cancel it and the noise level you would like to see to achieve a certain SNR, is of the range of 18 to 27 dB. And that is considered moderate, because if you compare it to active full duplex amplifiers, you will see later, those echo cancellation depths are much bigger. Moderate also because the echo actually is here at a smaller level than the signal, which is very nice in terms of properties, reduces the requirements on your echo cancellation tracking accuracy, reduces the accuracy you need to do in the echo cancellation coefficient, so it's a lot of increasing feasibility that allows you to design for. So that's for ALI cancelling amplifiers. If you then list up the pros and the cons of this option, okay, you regain the guard band capacity for sure. You go to virtual zero guard band, so you regain that half a gigabit or 1 gigabit of lost spectrum. There is still no full duplex interference, at least not of the CCI type, of the co-channel interference, because you're still doing frequency division duplexing, so that type of interference is not present in the network. There is still the other type of interference, like ALI and ACI, that's still there, but that has a lower impact, a much lower impact than CCI. It has moderate echo cancellation depth requirements, which means that it's a reasonably feasible technology to implement. And that's a little bit more detail, but if you're canceling out only the noise, you can also do schemes where you don't require any participation in all the echo cancellation training protocols, which are now required to do the training on the cable modems, do the training on the node. In this ALI cancelling amplifier, you could think about ways to not have that amplifier join or require any of those silencing mechanisms to do its training. A perceived con, of course, is unproven technology, meaning it has never been deployed before. And it does, of course, you do frequency division duplexing at the node. Then the last type of amplifier, so-called active full duplex amplifier. There, the big difference is that now, before you can amplify the downstream input signal, you have that upstream input signal, the echo there, of that signal, which is actually bigger than the signal that you want to amplify. So you need to get rid of that before you do the actual amplification. The big difference with respect to the ALI cancelling amplifier, you can do the same calculations as before, but you see the level of the echo that you're trying to cancel increases by the signal fidelity, which is roughly 40 to 50 dB. So where you previously had an echo cancellation depth of 20 to 30 dB, you now add 40 to 50 dB to that. So you have a 60 to 70 dB required echo cancellation depth, which makes things a bit more challenging in terms of feasibility, in terms of tracking, in terms of stability, and also implementation cost. But there is another property of active full duplex amplifiers that makes you think twice before deploying such an amplifier, and that's actually not related to the echo cancellation. So even if you have perfect echo cancellation, meaning you would have infinite SNR at the output, you have the aspect in your network of full duplex interference. So full duplex interference, the CCI, arises because the upstream signals of one modem overlap with downstream signals that another modem is trying to receive. And the standard has sounding mechanism for that. So with sounding, you measure that interference, and then you group modems into different interference groups, and they use complementary RBAs or FDD settings. So you say the modems that interfere, well, you will use upstream and downstream on exactly the same frequency so you don't overlap, so you don't cause interference to each other. Modems that don't interfere, well, they can overlap as much as they want, there is no interference. So
3.5 minutes.
Okay, I'm almost done. So if you do the calculations, the details are in the paper, you can actually show that the interference coming from modems after the amplifier to any of the modems before the amplifier is given by that formula there, which is the signal to interference ratio. P is the downstream transit power from the node. R is like the upstream PSD you're targeting at the node. And X1, as you can see, is the loss between the node and your tap location. The DIR is so-called tap directivity, so the difference between the isolation from output to tap and input to tap. And the insertion loss is the insertion loss of the tap, but that's not really crucial. If you plot this on a chart with the vertical axis being the signal to interference ratio, and the horizontal axis, the loss from the node to that next amplifier, you actually see that to achieve an SIR, so an SNR under interference of more than 41 dB, you can tolerate extremely little loss between the node and the amplifier. So for sure, some CMs before and after the amplifier will experience very high interference, and so they will be grouped in the same interference group. If you have a cascade of amps, that means that the whole cascade will turn into a big interference group, meaning that although you have full duplex amplifiers, you're going to use half duplex because they all interfere with each other and you use them in the same FDD or RBA configuration. So basically you have made your full duplex capability of the amplifier redundant in that case. There is a solution for that, and if you look at the formula, if you reduce amplifier spacing, or you reduce the X1, you can improve on that, or if you use taps that have extremely high directivity. But these don't exist today. Today they are at a 10, 15 dB of directivity. So pro, real full duplex operation, con, unproven technology, limited cascade depths, and no drop-in amplifier replacement. So to conclude, active full duplex amplifiers, it can be done, but you have to question at what SNR, and it will not require drop-in amplifier replacement unless you use extremely high directivity amps and have a way to reduce the loss between the current locations. So according to me, the future is either based on diplexer-based amplifiers or ALI cancelling amplifiers, meaning you would resort to FDD operation. Benefit there, you have no full duplex CCI interference, so basically you don't need full duplex processes like sounding and RBAs. If you have diplexer-based amplifiers, you still have the GAR band, and that needs to be traded off or compared to ALI amplifiers, which would have a 0 GAR band. But of course, it all comes at a cost. So you have to compare the extra cost of an ALI amplifier versus the penalty of having a GAR band and a cheaper diplexer-based amplifier. Thank you for listening.
Thanks, Werner. You know, I'm going to read his bio. I didn't get a chance to read it before, but I think it's a really good one for all you guys to know because I'm actually really happy on behalf of the industry to see some young blood coming into the industry. And so Dr. Werner Coomans heads the Copper Access Department within the Access Lab at Nokia Bell Labs, focused on next generation gigabit access technology and leveraging copper infrastructure. Now, when you hear copper and Bell Labs in the same place, that means twisted pair. So I'm glad to see we're getting people coming out of twisted pair and into coax. It's so much more exciting in coax, wouldn't you agree? There. He actively contributed to several standardization bodies such as ITU and Cable Labs, and was a recipient of the Bell Labs Outstanding Results Award in 2018, and received his PhD in the Fellowship of the Research Foundation Flanders, FWO, in 2009. He joined Bell Labs in 2013 after obtaining an MSc in Electrical Engineering in 2009 and a PhD in Engineering Sciences in 2013. So thank you, Werner. I'm going to go up as the second speaker. Let's see what it says in here about me. Oh, it's a better picture than they had on the IT, over at the IT stage. Somebody dug up a picture on the internet with me going like this and put it up on the screen. They quickly took it down and put it up another one. We had a backup picture on the slides. But I work at Cisco. I happen to be a fellow and a CTO of the cable access business, and I think my claim to fame is I started that business back in 1996, about 20 years ago. Matter of fact, this week is my anniversary week at Cisco. I've been there 30 years. So, thank you. I joined it as an itty-bitty little startup. When we got bored doing routers, we decided to go do cable. That was probably one of the best decisions we made. So I've done a bunch of stuff in the cable environment, including, remote PHY, DSG, modular CMTS, full duplex. I'm working on some small cell stuff if you guys are interested. And I'm part of the Hall of Fame and Cable TV Pioneer Society. By the way, if you didn't know this, on Wednesday night is the Cable Pioneer Dinner, and they decided that this is 20 years since the cable modem, DOCSIS cable modem, passed CertWave 6, I believe it was. So they're indoctrinating a whole bunch of DOCSIS people. They got about 10 or 15 DOCSIS people going through into Pioneer Society. So this is a really good week to be kind of proud of the early heritage of our community. And it's been 20 years of video people in there, and now the DOCSIS guys are getting there. Now, this particular, I should stop talking and figure out how to get the new white paper up here. Let's see. Start. New Orleans. This looks good. So this is a little bit of a bittersweet white paper. I co-authored this with a fellow by the name of Hung Jin. We were working on an FDX amplifier. We had been kind of working on it for 5 years. We were 2 weeks away from getting a prototype up and running. It was built. We were just waiting for software support to download coefficients and things. Then, due to the strange dynamics of the marketplace we're in, we had to make a really tough business decision, and that was to exit the amplifier and the tap business. So the project got shut down, and Hung, who was one of the most brilliant people I've ever worked for, we've lost him back to the wireless industry, which I think is a loss for the industry and also a loss of a good friendship. But he was a brilliant guy. Most of what you see in here is all his work. And what I asked him to do, since he was leaving and we're not going to build amps anymore, I said, you know what? Why don't you just lay it all out? Why don't you lay out the design of the amplifier? Like, it's your legacy. Tell us how it worked and what it did and what it would have done. So I'm going to try and fill in his steps and do that. So what is an FDX amplifier? We've got a lot of great backgrounds. If I hit any background slides, I'm just going to skip them. How the FDX amplifier actually works? What are the specifications in it? What are the DSP tricks we did with it? And what are some additional cool things you can do when you stick a DSP processor core in the middle of an amplifier? So let me skip the first two so I can spend more time. This is, really, an amplifier just has to do some kind of echo cancellation in both directions. And, an open question, is it analog, echo cancellation, digital, or both? And do the two different directions matter? We put together a specification for the amplifier. What we did is we took our gain maker node, which is already in the field, and you'll see if this laser works. Yeah. So this downstream here, this is just the gain maker node. We stuck that in here, and here's upstream legacy. That's the upstream power levels from the gain maker node. We then extrapolated that over to the upstream band. We put 8 dB of tilt in that. And Hung drives that two different ways. One is there's a 12 dB requirement, and you scale it back for the frequency range. And the other one is if you drop 4 dB over a 100-foot cable, you also get from 12 back to 8. So that is the power template that we were that we did meet. This goes through the losses in the output. So output would be towards the cable modem, towards the home, and input is towards the plant, even though both sides really have inputs and outputs. So you're going to have to twist your head around if you're thinking amps versus components versus directions. But this is really how all the power levels break down. This is completely described in the paper, so I'll just highlight a couple of things. But what we did is we took the output of the amplifier here, which is 72 dBmV over the full frequency range. The biggest reflection, you know, when you get reflections on the nodes and the amps, you get about 7 or 8 of them, all spaced out in time, which is why you need a time-based echo canceller. But the first one comes right off the case. I mean, it just doesn't waste any time about getting right in your face, right? So we found that we got a huge spike, 20 dB down. So you can see the spectrum here, coming back in, full spectrum here. There's a low-pass filter, so then it drops to partial spectrum, and then we have an echo canceller here. And if you look at the incident power, which we calculated out to be 24.5 dBmV across the FDX range of 108 to 684, and you compare that or you set the numbers, it turns out you need an echo canceller gain of about 53.5 dB. So slightly over 50 is the strength of the echo canceller that this path has to provide. That, of course, gets split between analog and digital if that is your implementation. And that's based upon the number I didn't include here in the calculation is the desired SNR ratio. So if you hook the gains and the losses and the performance you want, you just reverse engineer your echo canceller, which is just basically getting rid of the effective noise. And we can do it in the same direction. But what's really cool here to note is the power coming out of the upstream direction is not full spectrum. It doesn't go up to 1218 in the return path. There's less power, less TCP in the upstream direction. It's half the frequency, and it's less power in the direction that's being driven. So we have 54.1 dBmV across the 108 to 684. Now, what we didn't include is there's a little bit extra power here for the 5 to 85, but for simplistic, we just wanted to show the FDX operating. So when you translate this into product, take into account all the extra stuff that's running around. But it reflects around, if you go through the same type of calculation, you need about 52.3 dB, almost the same number in the opposite direction, which intuitively does sound correct. All right, so if you're going to build an amplifier, you have to somehow get 50 dB a gain in both directions. How do you build that amplifier? This is the schematic of our amplifier. Let me try and step through it. It's a little bit hard to see here, so let's see what we can do. Let's focus on the output port side. So one thing that you might be confusing is these are DACs and ADCs. It's the same symbol, the way things get drawn, even though one's a DAC and one's an ADC. I wish there was actually different symbology for this, but you'll have to squint, right? So what we end up having is, first of all, you have the downstream path here. So here we take the downstream path, bring it along. We apply, anytime you see an arrow with a C, those are coefficients. So you take the signal, apply coefficients to it, and then you can generate your analog echo cancellation rate here. Now, the reason you need analog echo cancellation is really to adjust the dynamic range of the signal so that when it goes into the ADC converter, you don't blow it out. The signal coming in, you know, the output signal that reflects back in is higher than the input signal, right? So that means it'll, you know, if you were to just blast it in the amplifier, you're going to have to, your input signal goes to a lower level, it's closer to the noise floor. So this guy's job is to knock out anything that impacts the dynamic range. So we usually go well beyond, you know, there's 7 reflections. We go beyond 2 reflections with our analog echo canceller. But we do have a cleanup guy over here. But we'll go through and basically cancel out 7 echoes with our analog echo canceller out here. We'll get it as clean as we can with the analog echo canceller. All right, so what's our next path? This is a subtlety that everybody seems to miss on building an amp. But when you have, or a node, when you have your signal coming in the downstream path here, it has a noise floor to it, right? When it goes through this amplifier, and when it goes through this D to A, it picks up an additional noise floor. And when it goes through this amplifier, it picks up more noise floor. So this signal coming down here that we just talked about, that canceled off the downstream, it only canceled off the signal here. It didn't cancel the noise floor being contributed by the amplifiers. And if you don't cancel off the noise floor, you'll never get past a certain performance margin of what the dynamic range is of that output amplifier. And you need that extra boost. So what we did in our design is we tapped, there's a tap here on both output amps. It comes in, we analog echo cancel it, believe it or not, to remove the signal from it, and also to get it in the dynamic range of the DACs. And so what we have is a noise floor coming in here. We take both noise floors and we bring it down here, and we subtract it from the return path signal. And then, of course, we have the forward path being canceled out right here. So we have a two-stage echo cancellation. Here is the path where the downstream comes down and is applied as an echo canceller on the noise floor. If we look at the other side, we see a path from the return path, coefficients being applied, going out through a DAC, and an analog echo canceller is applied. But you know what? We were able to build it without a downstream DSP in it. We got enough echo cancellation out of the analog echo canceller. And I think we have that. No, we don't have it in the next slide. But the way it really worked out is we have less TCP in the upstream, right? So if you have enough echo cancellation, there's less power, and you work out all the numbers, it just worked out beautifully. You didn't have to do a two-stage echo cancellation. So that does lower the cost slightly over what was done in a node. But at the end of the day, you still have all the ADDs and D-to-As. So we're not doing the noise canceling thing with the noise and the amplifiers and the return path because we have enough headroom, right? So that you can see it's an asymmetrical design, more cost on this side than on that side. Echo canceller training. You got to train everything, right? So we had a couple of clever tricks there. So what do you do normally? Normally you have a signal and you just shut down that signal so that you have quiet, or what's really background noise, and you would measure that, and you would measure what the reflections are when you don't have a signal present. So we worked out a way basically to not have to shut down the upstream or downstream to do training. It turns out, let's say you have a node and it has 4 ports on it. At any point in time and frequency, only one of those ports is used because there's only one cable modem transmitting at any one point of time and frequency. That means your other 3 ports are unused. They have empty mini slots in there. But every single one of those mini slots goes through your DSP processor, and if you can identify it's an empty mini slot, you can end up using that for echo cancellation training. So you can be basically in the background constantly training on all the empty mini slots in the upstream direction, which actually I think is the next slide, come to think of it. This is the output port slide. We did a different trick on the, depends on which way you look at this. There's an upstream echo canceller and a downstream echo canceller that need to be trained. So the other trick we did is in the downstream direction, it's a continuous signal in the downstream. And whenever we sit down at DOCSIS, we say, you know what, I think we should stick a training window in the downstream. It's like, ooh, that's going to add latency. And when do you know what it is? Well, it turns out there's a trick to be had. In the downstream, we have these scattered pilots, and the scattered pilots are well defined in the specification. So the trick really is to receive your downstream signal, create scattered pilots that are happening at the same time as the downstream signal, cancel those out, and create empty slots in the downstream. They're only inside your amplifier that they're empty, but they're empty slots, and then you can do echo canceller training of those empty slots. So here we see a wandering pilot going through here, and then on the right, we see the spot where we'd actually do our training. Werner mentioned about the interest in the static amplifier. This is kind of the reduced guard band thing. Can you put 2 things back to back and use echo cancellers for that? So we did a study on that. The answer is yes, you can. And if you take a look at the difference, you only have to worry about ALI in one of the directions, not the other direction, because of the way the power levels line up. In the downstream, where you have just a megaphone full frequency, you've got a lot of power coming back. But in the other opposite direction is not nearly as much of a problem. So we went back into this amplifier design, and there's really this right down here. Since you're not doing the common channel interference, you might actually be able to delete the secondary echo canceller in the return path and just go with an analog echo canceller in both directions. That's what our research basically showed us. And then you'll remember the echo cancellers we had for the CCI case, where this common channel had to be over 50 dB. Well, the gains here are 25 dB. You only need a 25 dB echo canceller for the output port and a 15 dB echo canceller for the input port. So it is less work on the echo cancellers. Now, how many gates does that save on a digital echo canceller? If you save the whole digital echo canceller, it definitely saves gates. There's one thing I forgot to mention that's also really, really cool. So this signal comes down here, and it comes down over here, and you have your analog echo canceller here, right? Now, there's a little bit of delay through here, but, there's a DSP delay for the coefficients and a D to A delay, so it takes a while for that signal to get through here. What happens if the echo slams through this amplifier, comes around, comes right back in, before you have a chance to cancel it? Like it's bouncing off the case of the box. So another little party trick when you go to build these things is you actually have to insert a delay in the downstream. You have to delay the downstream path slightly so that you can calculate the cancellation signal, which is for some point in the future, so you can cancel it off. We have another delay in the upstream that delays the round path echo as well, because, for this echo canceller. Now, once you have these two delays, and they're very small delays, you can manipulate the delays to have the forward path and the back return path completely symmetrical. You can build an active FDX amplifier whose symmetry is predictable. And so anybody who's been working on the timing task force knows we love things that are symmetrical because it doesn't distort timing. Okay, I think I'll step this build up. Oh, and one more thing. We have a DSP processor in the forward path and in the reverse path. What can you do? In the amp, technically, we only have it in the reverse path. What could you do with that? Remember the earlier statement that at any one point in time, we could look at the spectrum and we could say this time slot, this combination of time and frequency or subchannel symbol, there's a modem transmitting here. And all the other ones, there's no modems transmitting. We had that. And there's two ways to do that. You can look at the map and synchronize the thing with the map and know exactly what's going on, or you just measure the power level. And if the power level you don't trust a little bit, you can do a little bit of signature analysis on the type of energy that's coming through, whether it's noise or whether it's signal. But fundamentally, once you do that, if you're not ranging, you can turn all those other time slots off, except for that one time frequency spectrum that's coming through. So if you're at a node, three ports, if you, at any one point in time, 3 ports will be shut down, 1 port will be open to capture that cable modem, right? And at every single amplifier down the chain. So what you do is you massively reduce noise funneling. So if you have 500 households passed on your node, it's no longer 500 homes funneling noise. It's only the homes that are along a specific amplifier chain, right? And now what you get is observability of a chain to each particular home. You can actually do correlations between the different homes, and we can find out what amplifiers are behind. You can actually diagnose problems on each segment of your plant in between the amplifiers. You can go in and find out if a particular reflection is coming from something in the plant or what it is. Because guess what? You have a machine that is measuring reflections. So there's some fantastic P&M things that you can do with this. So not only, oh, thanks. That's remaining, right?
That's remaining.
Okay, good. So not only can you dramatically reduce noise funneling, but you can play other tricks with it too. I've got that on my conclusion slide. Oh, on the noise funneling. These echo cancellers are working on 108 to 684. That's where they brag. That's where they can subtract out full duplex. But they are wide band echo cancellers and wide band A to Ds and D to As. So we can actually go into 5 to 85 and clean up all the noise funneling in 5 to 85 as well. So the panacea of the cable industry, if you guys have been here for 20 years or longer, 30 years, everybody's always been wanting to clean up the return path noise funneling in the upstream path. This is a thing that'll do it. So in summary, both FDX, where you actually are canceling off co-channels, and static FDX, where you have adjacent channels, which I think we should not call static FDX, by the way, require back-to-back echo cancellers, and they share a similar DSP and hardware architecture. But of course, if you're not overlapping channels, you have substantial difference in the echo canceller gains. The GB is guard band, so it's a reduced guard band concept. In FDX mode, the downstream and upstream traffic is overlapping. The echo canceller is used to suppress common channels, and that's more than 50 dB. If you separate it and you're not doing that, you're at the 15 and 25 dB. But then the thing, once you have DSP in there, you can do anything your DSP imagination will provide you, right? So we talked about reducing noise funneling. You could do other noise suppression tricks. You could go in and if you had the energy, clean up OFDM symbols, right? You could go do tilt correction. You could, You could do it for ESD, you could do the dynamic digital diplexer. You know, if you're going to do a static FDX mode and have frequencies like this, you could really have any upstream, downstream cutoff that you wanted, right? So if there was 8 different ones, you've got it. And as far as the whole design goes, we fit this in one chip, by the way. The DSP and the 8 ADDs and DDAs fit into one FPGA, and we had it all built. You do need to be able to download code. So, you know, if you get really happy about this, we do need like a cable modem in there to download new software images into it, and a CPU to run that software. But cable modems are solvable problems. All right, with that, I would like to introduce our next speaker. And let's see, I'll spin the wheel here and see what... There it is. We'll see what SCTE has to say. So, yet another PhD on the panel. So what's interesting, you know, we've got two PhDs working on this, and Hung was a PhD. So we were honored in cable, really, to have like 3 PhDs working on the whole echo cancellation project. So Ayham Al-Banna is an engineering fellow and the Chief Technology Officer at Commscope, formerly Eris, if anybody didn't pick that up, where he works on defining the architecture for the cable access modules of current and future generation of Commscope centralized and distributed CCAP and CMTS systems. Dr. Al-Banna's work focuses on RF communications, HFC network architecture and migration, DOCSIS 3.1, emerging broadband technologies, etc. He has several issued and pending patents and has authored a book about characterizing and mitigating wireless interference in 802.11 wireless LANs. That should be a good one to read at night. Dr. Al-Banna is a senior IEEE fellow and has numerous publications in the area of wireless and cable communications. Please join me in welcoming Ayham.
Good afternoon. Before I start, I wanted first to take a moment and acknowledge my colleague Hang Jen from Cisco, one of the brightest engineers that I've met. It's very sad to lose him to the wireless industry. He's a very bright engineer, very good friend, and he contributed a lot to the DOCSIS 3.1 specification and the FDX specification. So just wanted to take a moment to acknowledge that, and you know, he will be missed. So thank you, Hank. Now, if I can get my way to get the slide to flip.
Yeah, using the arrow or something.
All right. Okay. So I'll be talking today about you know, full duplex DOCSIS and what we call soft FDX or soft FDD, along with extended spectrum DOCSIS. All of these technologies are complementary in nature. So I'm hoping I'll lay the ground for the migration strategy section toward the end of the paper. I wanted to thank my colleagues, Dr. Frank O'Keefe and Dr. Tom Clunan, for their support and contributions to this work. The paper turned out to be a 60-page white paper, so a lot of details. So I tried to make it shorter, but I could not. You know, there's so much going on in the cable industry, so I thought a good background to the story and some details to the solutions would help. So if you like, you know, an article that kind of puts you to sleep before you go to bed, you know what to do now. So this is kind of the full agenda, many topics. I'm not going to cover all of that because I just wanted to give you a sense of what the paper includes. These are all of the topics that are discussed in the paper. Starts with FDX, and then it talks about some of the inefficiencies that are introduced by the FDX specification from a modem viewpoint and ways to solve those. And then I talk about full duplex DOCSIS for cascaded networks and the challenges with that. Werner and John did a great job on introducing that topic. And then I talk about soft FDX, which is a topic that we are proposing as a way to get the benefits of FDX without actually doing FDX for cascaded networks. And I show some simulations to show how this soft FDX scheme is kind of equivalent to the FDX, and you actually get the benefits. In the paper, we propose an FDX taxonomy. You know, wherever you go, people just throw in terms, including us. So I had a figure there to explain what people mean when they throw in the various terms. And then I talk about video signals and out-of-band signaling. And I have a section for the extended spectrum DOCSIS, and then network migration strategies. So I have a slide or two on these, on each of these subjects that I will skip. Just wanted to leave that as an offline material for people to review. I will only focus on 4 or 5 slides that are kind of the key message of this talk. You probably don't know what FDX is. I just wanted to introduce it to you. FDX is full duplex DOCSIS, and it's basically allowing the upstream and downstream to overlap in the range between 108 and 684. It's a great technology. The only concern with FDX that when we created the specification, it was optimized for N+0, meaning no amplifiers. So that was one of the constraints. And then we started thinking, okay, what do we do? Many MSOs cannot get to N+0, so we have cascaded networks, so we need a solution. So we started working on FDX amplifiers in the committee. And we had 2 proposals. One of them is a TDD approach, where the amplifier switches direction. And the other proposal was a true FDX. This is what John showed. Now, there are multiple issues that we need to solve with FDX amplifiers, including cost, real estate, thermal issues, complexities. And if we assume that we solve all of these issues, then also physics came into play. There's a problem that introduced itself when you use FDX amplifiers, which is the fact that FDX amplifiers amplify interference in addition to the signal, which makes all subscribers being in the same interference group, which means you cannot do true FDX with that. Now, you can try to cut the distance in half and put another amplifier, and then you still have more interference groups and do FDX, but that will be an unrealistic solution. So now if we started with FDX, it's N+0. We created FDX amplifiers, but they cannot enable FDX with cascaded networks. So what is the alternative? The alternative is something we call soft FDX or soft FDD. It is basically running your network just like today in an FDD environment, frequency division duplex, where the upstream and downstream are not overlapping. You have the upstream and the downstream is next to it. Now, where is the soft piece coming in place here? Soft means that you have the ability to change the split using software. The separation between the upstream and downstream, you slide that through. So for example, you can have an 85 megahertz split, and then you decide to move it to 204 megahertz or 300 or 684 for that matter. You can do that with software, maybe using a CLI command that is issued from the head end. So soft FDX, in that sense, this FDD network is easy to manage because you don't have overlapping downstream and upstream. It is a special case of FDX. If you think of FDX, where all modems on that node in one interference group, then this is what you get. There's no FDX. Modems next, the modems will use the spectrum in an FDD fashion. So this is actually a special case of FDX. Now, there are two ways you can use this proposal. You can use it in a static mode, static soft FDD or static soft FDX, which means that I select a split, and then a year or 2 years later, I decide to change that split. I can issue a CLI command and then move that split, as opposed to rolling a truck to modify that split. The other way to use this proposal is dynamic soft FDX, where the core that has the scheduler is smart enough to move the split around based on the traffic. So if I have an upstream test, speed test coming up, then it will increase the split. When that is over, the split goes back so that you can reclaim the downstream spectrum that was lost. Some people may choose to do static soft FDX, where they say, okay, I want to issue a CLI command, I would like to have full control, make the split larger, but that will come at the expense of losing some downstream spectrum. Now, this is where extended spectrum DOCSIS come in place. This is where we need to go to 1.8 gigahertz in order to compensate for the spectrum that we lost in a static soft FDD mode. This is where you see the technologies are complementary. So this soft FDD scheme works hand in hand with the extended spectrum DOCSIS. Now, somebody might say, okay, why do I need this soft piece, to change dynamically? It helps you buy time. So if you have this dynamic switching, you can reclaim the downstream spectrum, then you go back and you make the upstream larger. It's dynamic in nature, which means that you are not forced to go to 1.8 gigahertz right away. It buys you more time. It gives you the benefit of FDX because you're able to reclaim the downstream spectrum. Downstream goes back to 108, so you have access to the full downstream spectrum between 108 and 1.2 gig. And we need that for the upstream. You just make the split larger and back and forth. That will buy you more time before you need to go to 1.8 gigahertz. So that's kind of the soft FDX scheme. I'm showing some simulations here that, if you choose to do static soft FDX, meaning change the split and leave it alone, then obviously as the split gets higher, you have higher upstream capacity, but that will come at the expense of the downstream capacity. And this scheme, by the way, works for cascaded networks, and we simulated that for up to N+5 for this work and more cascades in other work. Now, if you do dynamic soft FDX, or dynamic soft FDD, where you have the ability to go back and reclaim the downstream spectrum all the time, then it becomes equivalent to the benefits of FDX. You're still not running FDX. This is still FDD system, but you get the benefits of the FDX without the need to go to N+0. So this is just a quick figure to show you the different terms. You can go through that offline. I say hard FDD is where you need to the amplifier location or the node and change that diplexer. Soft FDD or soft FDX is when you have the ability to do that with software. And again, this is kind of part of the special case of FDX, can be looked at it that way. And then there are issues with video signals and out of band. They are discussed in the paper. Extended spectrum DOCSIS, as we mentioned earlier, extended spectrum DOCSIS works hand in hand with the soft FDX scheme, or the soft FDD scheme. Now, just wanted to let people know that, if you have a tap that is rated, for example, to 1 gigahertz, it can perform beyond 1 gigahertz. It's not like a cliff. So you can push energy. You can use that roll-off region with the DOCSIS 3.1 variable bit loading and multiple modulation profiles in order to get more capacity and buy more time before you push the spectrum beyond what you actually have, which is free capacity. Again, when you have soft FDX in a static mode and you grow the spectrum in the upstream, that happens at the expense of the downstream, and therefore you will need to push your downstream spectrum, beyond 1.2 gigahertz. Then somebody will question the idea of going to 1.8 gigahertz, and they will say, okay, well, how are you going to come up with the additional power? We have limited TCP power that we use today. We have limited power that is coming to the amplifiers and the nodes. How are you going to come up with the additional power that is needed to go to 1.8 gigahertz? And we are saying you don't have to increase that TCP. We are proposing to keep that TCP to be the same and identical to whatever we have today. It is just the exercise becomes being creative in how you distribute the power that you have over a larger spectrum. And our proposal here is to keep the power up-tilted over the range of single-carrier QAM channels and video channels, and that will help with legacy devices. You do not need to respace the amplifiers. It will be seamless for them. And then beyond the spectrum region, where you have single-carrier QAM and OFDM and video channels, become your OFDM channel region, or channels for that matter, and then that power spectral density is flat. So you can see it's straight up tilt and then flat in the OFDM. And then somebody comes up and say, well, the signal will be degraded by the time it gets to the modem, and it will be down tilted, and the SNR will be down tilted. And we say, well, that's all right, because we worked hard on the DOCSIS 3.1 specification, and we included the variable bit loading feature and the multiple modulation profiles, and we can use that part of the spectrum with no errors. So this is kind of capitalizing on the best of the two worlds, being seamless migration for older legacy devices, and then capitalizing on the 3.1 technology that spent 5 years working on. We did simulations for 1.8 gigahertz and 3 gigahertz systems in the paper, and we also did sensitivity analysis, versus the TCP. And yes, a little bit higher TCP might give you better throughput, but increasing that a lot might hurt you sometimes because the distortion of the amplifiers start to kick in. Obviously, longer plants will have lower throughput than shorter plants. That's expected. So, the paper has a lot more simulations and more detailed description of what we did. Finally, here, I wanted to show a migration plan where, people can use it, hopefully, in deciding what to do next. So today, I'm thinking we should go to DOCSIS 3.1. That's a must in my migration plan, or you cannot die. After DOCSIS 3.1, you can change the split to a high split if you want to buy more time. You bond single-carrier QAM channels and OFDM channels, and then you get to N+0. And you start asking yourself, am I at N+0 or not? That's a question. That's not a state. If I'm at N+0, then I could probably do the traditional FDX if I choose to. And if not, which is likely the case for many MSOs, then you ask the question, do I have true FDX amplifiers that can enable true FDX? The answer is no, unless I cut the distance in half, which means the next step is using the static soft FDD in that case. If I do static soft FDD or dynamic, am I tight in terms of my downstream spectrum? If my downstream spectrum is tight, then I might want to go in the roll-off region or do the extended spectrum DOCSIS. And then you go to active tabs, fiber to the tab, and fiber to the home. In the paper, I did two scenarios for migration. One scenario for the N+0 MSOs, of how that might progress between today and fiber to the home. And the other scenario for the MSOs that have cascaded networks, where they will be able to, go through the various steps here with, like, for example, 3.1, again, change the split. Am I N plus 0? No. Do I have an FDX amp? No. Then go to static soft FDX. Or you can choose to do dynamic. But if you choose to do static soft FDX, then you ask yourself, is my downstream tight or not? If that is yes, then you have to come up with a solution. And that will be going to the roll-off region and then extending the downstream. In conclusion, wanted to say that our cable industry now is in a good state, in a good spot to see the vision into 10G. We have many technologies. We have FDX in N plus 0. We have the soft FDD, and we have the extended spectrum DOCSIS that all of them are part of DOCSIS 4.0. All are complementary technologies, work together. They use the same silicon on the modem. So all MSOs will be kind of coming back together using the same technology to offer 10 gig down and 5 gig up with this DOCSIS 4.0 revision. And obviously, if we want to get higher upstream speeds, we'll need to change the spec a little more. And with that, I wanted to thank you for listening, and we'll be here for questions.
Thank you, Ayham. So there's a microphone in the middle of the floor. We have 15 minutes for questions. I'll post a question to you guys. Does the industry need this? Should vendors go build it? Right? Do we do the FDX amp for either FDX or ESD or both? What should we do? Anybody has an opinion one way or the other, please step up. Or any other question, please step up.
I'm just thinking about what you're saying. So my question is, if you go to the N0 plus 4, what is your modem count that you're looking at? I mean, N0, we're going down to 35, 40 homes pass. But if you go to the N plus 4, what are you looking at as far as the modem counts that would be in that cluster or that group, that node?
I mean, it'd be the same as the modem count we have today for an N plus 4. We'll be looking at trying to fit into an existing network. So I don't know if anybody's got good N plus 4 numbers. My numbers are usually around 300 or so.
So you're still, okay, that's what I was just wondering
Yeah.
what the count was. All right.
Yeah.
I mean, the question that you just posed to us about, whether there's a need for this kind of technology to go down this road, doesn't it really just come down to, if you've got to build fiber out enough to get to N plus 0 or N, to add the nodes to get the fiber out there to do that, is it more cost effective to simply just build fiber to the home and,
Well, in this scenario,
call or quits?
That's a good question. So there's multiple scenarios there. You pull fiber at N plus 0, then your question should just keep going. And I think there's an exponential number where it just keeps, there's just more billions of dollars to get to that home. So studies have shown, and Comcast has done a great study on that, that seems to be a cost-effective approach. However, I think you don't need an FDX amp when you do that. The FDX amp is really leave the fiber that exists. Go with your N plus 4, N plus 5 network, and upgrade the amps. So then the cost equation is very interesting. You don't have to spend money on fiber, you get to spend the money on the amplifiers, right? And that should be a lower investment. But at the end of the day, if the cost of the amplifier doubles, is anybody going to buy it? Like amps today are $400 to $600. You put a processor there and a FPGA and stuff like that, I don't know what it'll come out to, but let's say it's double. Let's say it's $1,500 instead of $600. It's saving you a lot of money, but will people actually go out and buy it, or is it a stillborn product?
I would like to pitch in on that. So also coming from a DSL business where this increasing fiber penetration depth is more a usual way of working, it all depends on the business case, as you say. So in some countries, depending on labor costs, depending on whether you have aerial fiber, buried fiber, all these variables come into play. And basically what you have, we as a company, Nokia, we sell everything. We sell cable, we sell DSL, we sell bond. So basically it doesn't really matter for us what you choose. But we see that operators, depending on where they are, what the conditions they are under, have an optimal fiber to the, what we call the dollar, fiber to the most economical point. In some cases it makes sense to do fiber to the home. In other cases, it doesn't. So it's really depending on all those variables whether or not.
So, Rob.
Yeah, so I don't usually come to these sessions getting asked questions on this side, used to going that way, but it's a good question. I mean, I think obviously the more inexpensively we can deploy FDX, the better. And if N plus 0 creates a cost barrier and N plus 1 helps improve that, I think that's valuable, of course. There's been a lot of studies done on cost delta between going to N0 and going to N1 or going to N2, or, you know, the opposite, not the opposite really, but the BAU model that gradually gets you there. I mean, I think we all have, on the MSO side, a good idea what those cost parameters are. What we don't really have a good feel for is what the cost and complexity of these amplifiers are. I don't think there's enough work there done to answer your question directly, but I think there's a lot of good work left to be done to answer that. That topology that you put up there, sorry, Hangjin's not here to give us more details on it also. He was a really solid engineer. Yes, it's not like rest in peace, I guess, right? He's in another industry. He's doing wonderful things, I'm sure. But it's important for us to understand the operations of that amplifier, the cost delta of that amplifier. Certainly, pulling fiber versus a CapEx expense for an amplifier, these are two different things that we can sort of balance those numbers if we know what they are. I just don't have for our side, I don't have a good feel for what that amplifier looks like from a cost perspective, what setting up that amplifier looks like in the field. An amplifier is a pretty simple, dumb device today, so we're adding some potential complexity or potential smarts that remove complexity for us. I'm not sure how that works out, net. I just sense that there's still work to be done in the amplifier side to really quantifiably answer your question. I can tell you that we're interested in knowing if we can, if we want to build N plus 0 in an area and it's lower density, then we'd prefer to have it built, and we could throw an amplifier in there. It makes it harder to go ahead and do that if we don't know that an FDX amplifier is coming along later for when FDX comes, right? That's the math we do.
Yeah.
So
I mean, we have the numbers, had the numbers behind that to basically put together. But I would actually, I'll play an analogy, right? So it turns out in order to put FDX in the node, you have to put software in the node. To put software in the node, you have to make it IP addressable, so you need a cable modem in there. The same is true with you know, the intelligent node, the intelligent nodes. Now, we end up getting it because we already have a direct IP connection, but we jazzed up the intelligent node by putting extra DSP chips in there. It was more money, but there was more value. And you could look at the intelligent node as like, even if you just completely ignored FDX, if you wanted to put some of those spectrum analysis chips in there and figure out which port noise is coming in, you could do all sorts of things. And the simplest implementation of that might be a cable modem with a bunch of A to Ds and D to As and DSPs that just did digital signal processing. So it's almost like a Swiss Army knife. Once you invest in the DSP and the Ethernet, you get a huge amount of value. And FDX would be actually a very minor increment to the rest of that value. So if the rest of those solutions have value, then FDX is this extra one. And how that judgment call is made is an interesting
We've done quite a bit of
site.
sensitivity analysis around if we added an amp or two and it costs 1% more, 10% more, our max is, 12% more, I'm kidding, 20%, whatever that number is, what's that multiplier? And build the same, and look at a footprint and say, if I built it N plus 0, it'd be this, if I built it N plus 1, it'd be that, from a CapEx standpoint. What does that delta look like? Is that valuable enough to go, do we save enough in doing that with the amplifier? Or do I have to go back later in 3 years when FDX is around and replace it with a node because an FDX amplifier doesn't come along to solve that problem? The other thing, and this was mentioned by all of you guys, it's, the amplifier is one thing. The other part is how do you solve the interference group elongation issue? So there's ways to solve it.
With the what?
The interference group enlargement that happens. If we have to change the architecture a bit to do that, that's another variable to play with, right? If we have to shorten the runs or change the tap directivity, those are things we have to take into account. I'm sure you know the work that Dr. Coonan actually did on that interference group sizing thing is actually pretty favorable for a while at least on how large that interference group can actually be before you start to have to worry about it. And that could buy us some time towards getting technology in place that's there when we need that kind of granularity. When we need tap level granularity of an interference group, it might be a ways out. And the amplifier might not be in the way for quite some time because of that. So,
Yeah, it was, actually, I didn't put a slide on that, but it was in our white paper as well, where it was not as ideal as multiple interference groups per segment, but it was manageable if you had multiple ports going on a node. You You could multiplex within the first segment and multiplex across the nodes, and then you could combine different interference groups together depending upon the modem population. Workable, not perfect and beautiful, but workable. But thanks for your input, great input. I would also say that all these questions still exist for the DOCSIS 4.0 work, where they're basically looking at an identical amplifier to this, but to do a switchable return path. All right, so I'd say the question still exists. Bill?
Yeah, a couple of comments. One, yeah, I think we are interested in amplifiers. If we go to symmetric services, high bandwidth symmetric services like 1 or 2 gigabits per second in the future, we're in the situation where you're going to have to devote quite a bit of bandwidth to upstream. From the previous session, Ayham's colleague, Tom Cloonan, spoke about the traffic engineering involved and the ability to do dynamic switching of the upstream and downstream that you could do with an echo canceling amplifier. And one of the things there is the ability to share this Tmax, the highest bit rate that you have to achieve only occurs very infrequently, and being able to share that bandwidth between upstream and downstream allows you to potentially extend the life of your current architecture of the plant if you're using echo cancellation versus having a fixed diplexer where you're going to have to keep it at that point. So I think that's something that figures into the overall cost of what an echo canceling amplifier brings to you versus having fixed diplexers in the system. So it's something that has to
that's a
be
good
worked into
point.
the equation that's, I think, favorable towards an
Good.
echo canceling amplifier.
Yeah, we call it FDX Amp, and that's because it originated out of the FDX camp to solve this particular problem. But if you look at it from a product point of view, and as a Swiss Army knife, it'll probably have 10 features in it, with FDX being one of 10 features. So are those features, 10 features as a collection, have the value that's worth building and shipping a product? All right, I think we are at the end of our time, so I'd like to thank everybody for showing up today, and enjoy the rest of the show. There is an FDX panel, by the way, tomorrow morning with 2 more FDX papers, or tomorrow morning? No, Thursday morning. Yes, and then Bill will be presenting. So you want to come listen to him. And Nader from Shaw will be presenting. It is at 8 a.m. in the morning, so if you want to sleep overnight in the hallway, you're welcome to, but I'll probably be showing up around 8. Thank you.